well, try to answer this question at least partially, of how ubiquitous is entanglement in QFT, which is a project that I've done together with my two thesis advisors, Ivana Agulló and Beatriz Bonga, and also with two amazing collaborators and friends, Dimitris and Sergi. So let me start this talk by giving a brief motivation. And the motivation of this talk is coming from a well-known, well, maybe not so well-known, result in quantum field theory, that is the Reeh-Schlieder theorem. So let's consider a free scalar field in 1+D-dimensional Minkowski spacetime. And I'm going to consider the set of smeared operators defined like this. I think that you have already seen this particular form of smeared operators before, where these functions f are smooth and of compact support, or at the very least of compact support. So something that I think everybody will find more or less, fact that it's intuitive, is that given the vacuum state that I'm denoting with this sketch, states of this form here, where I'm applying several kinds of these operators for Fn, whatever n is, suffices to generate the Hilbert space of the theory. What it's maybe not so, intuitively reasonable, and it's the content of the Reeh-Schlieder theorem, is that this previous statement, namely that we can generate the full Hilbert space of our theory just with states of this form, remains true, even if I restrict all these smearing functions of compact support to be supported in a small region, as small as I want. Okay, not so many surprise faces, so let me just put an example of what I'm saying with this theorem, for those of you who are not familiar with it. So let's assume that we have a very advanced and nice quantum lab here on Earth. That is, the only requirement is that, it's here on Earth, so it has a finite dimension. And that is such that it can create any quantum operator we want, not necessarily unitary operators at this. And let's assume further that there is a state in the Hilbert space of our theory that contains the Taj Mahal at the back of the moon. What the Reeh-Schlieder theorem is telling us is that by, creating one such operator inside of our lab here on Earth, and acting with that operator in the vacuum state of Minkowski, we can basically generate this state with the Taj Mahal at the back of the moon. Okay, this is really surprising, right? And no wonder that one can ask, okay, what's going on here? What is the reason that we have such a nice result? And the reason, not surprisingly, since this is a talk about entanglement, is entanglement. So basically, the lesson that one extracts from the Reeh-Schlieder theorem is that entanglement is ubiquitous in QFT. It is everywhere. However, there are some catches in this statement. And one of these catches is, what does this statement mean in practice? And why do I mean by in practice, right? Well, as we all know, a quantum field hosts infinitely many degrees of freedom, even if we restrict attention to a finite region of spacetime, right? But when we interact with a quantum field in any way, we really don't have access to all these all these infinitely many degrees of freedom of the field. Rather, the image I have in mind of what happens when we try to, interact with such a field is that we do so with certain measuring apparatus that are made of a finite number of pixels, such that the image that we can really, or better said, the information that we can really gain from such a quantum field is something more like what I've represented here in, in the screen of this computer, right? So kind of a simplified and smeared average version of this field, or these degrees of freedom. So let me now try to answer the question of how is entanglement, or how ubiquitous is entanglement for this kind of systems with finitely many degrees of freedom, the kind of systems that, at least in my opinion, can be regarded as somehow more physical. So the first thing I want to tell you is how do we select these degrees of freedom? Since we are, talking about free theories, I can either use the covariant formalism I presented before, but I can also use one that, to my opinion, and for my purpose, is a bit, let's say, more convenient, which is basically using the canonical formalism and defining a single degree of freedom of the field by taking two operators, a field and a momentum operator, smeared with corresponding smearing functions that, for simplicity, I'm choosing to be the same. and such that in this case satisfy canonical commutation relations. Also, all the results I will present in what follows will be in the vacuum state, so Minkowski vacuum, which is a Gaussian state, which in particular means that the subsystem comprised by this degree of freedom is also a Gaussian subsystem. And as was mentioned in a very nice talk some time before the break, this also means that the subsystem of this degree of freedom is fully characterized by its covariance matrix, which I have also written here. But to talk about entanglement, I need to go to systems with at least 2 degrees of freedom. So let's do exactly the same thing as I was doing before, right? So I'm selecting 2 regions of compact support in a Cauchy hypersurface, and in each of these regions, I'm choosing a smoothing function. Technically, I'm choosing a smoothing function for field and momentum operators in each of them, but to keep it simpler, I'm choosing just the same function. Okay, so same story as before. Once again, the full system of 2 degrees of freedom can be characterized by its covariance matrix. And so once I know the covariance matrix, I can start computing entanglement. One of the catches of all this story, however, is that the reduced state that characterizes this system with a finite number of degrees of freedom is mixed, which in particular means that we cannot really use the von Neumann entropy of the reduced state of subsystem A and subsystem B to characterize the entanglement between these subsystems A and B. So, not such a big deal in this case, because we have other entanglement measures that we can use. And in particular, I'm going to use logarithmic negativity that has also been introduced very nicely in previous talks. Again, all these smoothing functions could be whatever thing I want, but for the purpose of this talk, just to make things simple, I'm going to choose a particular family. And I'm choosing this particular family of smoothing functions simply because they will allow me to perform most of the calculations I'm going to present analytically. So, they are kind of convenient. And I say that this is a family because it depends on a parameter delta, which is basically larger than 0. And this parameter delta, in the end, what it's doing is characterizing the shape of this smoothing function. So in a sense, in this case, I just put the functions normalized to 1. It's not the case because of this normalization depends or is fixed by the canonical commutation relations in practice. But the important point maybe is to recall that functions with smaller delta have more support near the boundary of the region that I'm going to consider. So now let me summarize some of the results that we have obtained in all this story. And again, let's keep things simple and let's take 2 degrees of freedom when D, the spatial dimension, is equal to 1. And I'm taking 2 regions. In this case, these are 2 lines of half length R separated by a certain distance rho, that is basically the distance between the centers, normalized in units of the radius of the regions, or half length in this case. Then, as you can imagine, the minimum distance that we can have is equal to rho equal to 2. Technically speaking, it should be always larger than 2, but in the limit when it closes to 2. And what I'm going to study, in this case, let's say I'm only going to present numerical results. And the reason for that is that for massless fields, there is this well-known infrared divergence in the 2-point function. So, I'm using a mass to regularize this 2-point function, but in that case, I don't have analytical solutions, sorry. But in all other cases, don't worry, I will present analytical solutions. And so the first thing I wonder was, what is the effect in the entanglement of, the mass of the field? Once again, normalized to the units of the radius of the regions. And this is what I found. This is log negativity as a function of the mass parameter of the field mu. And the first thing that, at the minimum possible distance between the regions, so in the limit when they are touching each other. And the first thing I noticed is that, first of all, log negativity is different from 0 for some smoothing functions. Again, not surprising. The entanglement we find depends on the details of the smoothing functions we use. So the real degrees of freedom that we're extracting out of a region with also as many degrees of freedom as we like. The second thing we noticed is that log negativity reaches a plateau when the mass of the field is small, but then it decays very quickly when we increase the mass of the field. So, well, the next thing that we can consider or that we can ask is, how does entanglement behave as a function of the distance? And well, this is what you see. So this is entanglement as a function of the dimensionless distance for a fixed mass corresponding to what? Well within the plateau. And what you can see, and it's the only thing that I'm going to mention about this result, is that it decays very quickly, and it dies completely after a finite distance. Okay, so that was encouraging, but now 1+1 dimension is maybe not the funniest example. So let's see what happens in 1+2 dimensions. So once again, we can do exactly the same procedure. So in this case, I'm taking two regions, which are these two circles. I'm choosing as many functions, one on each. And I'm asking what is the entanglement that there is between families of modes that I'm defining out of these Smithing functions in these regions. And nicely, I do have analytic results for these massless fields, when the fields are massless. But what we find is that there is no entanglement between these 2 degrees of freedom for any representative of that family. And actually also for other families, but I'm not going to present them here because of I don't have too much time. So then it was interesting, right? This was the first indication that maybe entanglement or its abundance depends on the dimension of the spacetime. So one thing that we wondered was, look, okay, maybe when we are taking 2 degrees of freedom, the entanglement is becoming too diluted, so we cannot find it. And then we started wondering, okay, and what happens if we consider larger families of degrees of freedom? Like this configuration, for example, in which I'm taking n, basically 2 n regions, and I'm splitting them into groups. One group of the red regions, where I have a certain Smithing functions, and another one for the gray regions. And then one thing we can ask is, what is the entanglement between all the degrees of freedom in the red regions with respect to the entanglement of the degrees of freedom of the gray regions? And what we find is something like this, which I think is nice because, first of all, entanglement increases linearly. And second, even though it's maybe not very noticeable here, we need a minimum number of degrees of freedom in order for entanglement to show up, which was, I think, the most interesting result we extracted from this configuration. And since it's nice, let me also show you another configuration with the same idea. In this case, what we are considering is a system made of a single degree of freedom in the middle, and we increase the number of degrees of freedom for the other subsystem around it. And what we find, again, is that we need a minimum number of degrees of freedom for entanglement to start showing up. And in this case also, that entanglement saturates quickly because, like the outer modes are just too far away. So finally, let me quickly tell you what happens in 3 dimensions. I'm sure you will not be too surprised when I tell you that if we take 2 spherical regions, we also don't find entanglement between any 2 degrees of freedom for all the families we have considered so far. Not only the one I presented, but also others. And again, the same story, we said, okay, maybe, too few degrees of freedom, so let's increase it. Let's play a different game. So we started considering families like this one, or this one, with thousands of degrees of freedom. And in this case, I can tell you that we also didn't find entanglement in these configurations. Not surprisingly, because packing spheres in 3 dimensions maybe is not the best thing we can do in terms of density to keep the most close. And actually, we do find entanglement for configurations such like this one, which is kind of the best thing we could think of. So we have a mode in the middle, and then we consider spherical shells around, and we have a Smithing function in each of these shells. But the point I want to make here is not that there is no entanglement. We know that there is entanglement that is warranted by the Reeh-Schlieder theorem. The point is that when we consider finite numbers of degrees of freedom, it turns out that entanglement is considerably less ubiquitous than we had originally thought, and that previous results in the literature seem to suggest. So even in this configuration, which is somehow optimal, it was hard to find entanglement in the sense that we had to fine-tune the parameters of this configuration, and also of the Smithing functions that we were using. So let me quickly conclude that, where all this story is going, and it's that we know that entanglement is ubiquitous in QFT, but it is surprisingly difficult to find for systems made of finite numbers of degrees of freedom. In other words, we think, or what we have found is that entanglement is there, but it's distributed in a subtle manner. So the thing is, we can find it easily by either involving infinitely many degrees of freedom, and I think that that's something that some people here are quite familiar with. But like my point is that that might be experimentally impossible at some point. And the point is, we can also find it with a finite number of degrees of freedom, but only by fine-tuning these degrees of freedom. So it is actually more difficult to find than we originally thought. And finally, what we found is that this entanglement depends on the space-time dimension. So it's harder to find with increasing space-time dimension. So that's all. Thank you very much.
So I see quite a few raised hands, Edu. And if we've got time, we could say.
Hello. Okay. Thank you, Patricia. Great talk. I like it a lot, as you know, and I like your work. There's one thing, if you can go back to the conclusions, that I'm like not fully agreeing with how it's worded, right? So as you know, right, there's also more entanglement structures that one can think of, just multipartite entanglement and so on.
Exactly. But,
And so let me just give you a prompt for you to talk about it. We know in principle that when you couple up all these talks about harvesting, right, you couple particle detectors,
yes.
just two finite, actually 2 degrees of freedom, really, and you couple them to the field alongside a time-like trajectory, right? They do harvest entanglement. So maybe you can talk a bit about it.
Yes, I will be very happy to do so. The thing is that we have also been, as you perfectly know, we have been also been thinking about how our kind of results match with entanglement harvesting. And our view at the moment is, we can reformulate more or less harvesting in terms of this kind of canonical formalism, in which case we are just exploring a large family of degrees of freedom. And even though we might not find, pairwise entanglement between these modes, we believe we have strong, let's say, we are quite positive that we will find multimode entanglement, so that, as I was mentioning, entanglement distribution seems to be quite simple. And this is something that we still want to learn more about.
Okay, so another question there at the end.
Thanks. Could you remind us how you constructed row AB?
Yes. Okay. So the thing is, in this point, and the nice thing is, I don't need to construct the row AB. You know that there is a way of doing it. And if you want a reference where this is done explicitly, I can recommend one by Bianchi, called, I think, von Neumann entropy of finite-dimensional systems. But the point is, you don't really need to, because for Gaussian states, this characterization of rho AB is exactly equivalent to the covariance matrix formalism. Well, okay, okay, yeah, exactly. So for the purpose of this talk, is sufficient to say that we can characterize these modes with the covariance matrix, and it's kind of easier to compute that. So that's why I don't have the explicit, explicit expression for rho AB.
We've got another question there.
Yeah, my question is, how is this Reeh-Schlieder theorem consistent with the notion of effective field theory? Just to remind you that, if you integrate, for example, ultraviolet degrees of freedom, you get an effective infrared theory, perhaps together with some stochastic noise, which then describes, and then the idea is that, there is an approximate coupling between ultraviolet and infrared, and that's, in other words, all field theories, as we know them, are effective field theory because they either lack ultraviolet or infrared completion.
Okay, this is an excellent question, and to be honest, I think I should think about it a bit more. But I can tell you, for example, about the Reeh-Schlieder theorem. I'm not sure if your question goes through this line, and I apologize for that. Is that, when I put that example of creating some states that act seemingly not locally, I'm talking about operators that are not unitary. So I don't know if that partially helped us answer your question. Sorry.
I don't know. Maybe we can discuss in the trial. Just also one comment when you said that the commutator of your variables now in terms of what you call FA,
yes,
the canonical pair. If you really want to take a proper, if you really want to say that you have the same degrees of freedom in both left-hand side and right-hand side, then there should be a notion of Dirac delta, because you have you know, to count degrees of freedom on the right and the left properly, you know, there should be Dirac delta on the right-hand side.
You mean in this expression, maybe?
Yes, yes, in the
Okay.
commutator.
The nice thing about this thing, well, the thing is I'm working with smeared operators, right? So in the end, the commutation is normalized to Kronecker delta. And this commutation relation is guaranteed by a choice. I agree with that completely. And it's a choice of normalization of the smearing functions I'm using. I should have said that.
Yeah,
more
it says that as well.
Okay. So thank you very much, Patricia.